So, hello and welcome. Hello again. Oh, my mustache is... Anyway. Hello. I gotta shave it. I gotta give it a shave. It's getting out of control. So, hello and welcome. Sorry, you're gonna have to forgive me. My mind has been all over the place lately. I've just... Oh! Too many things. Too many problems. I think I've succeeded in making my life a lot harder than it needs to be for myself. Successfully made things more difficult than they need to be. You can imagine that. It's always good. Anyway, so all right. The deal is we have a problem that we were looking at the other day, and I've been struggling with this problem. I have an idea. I have two more ideas that I can try. One idea would be to combine the previous idea that I had to just kind of take the lowest cost item, sort of one at a time. Excuse me, and the other idea is to do a backtracking approach once we get to just a few subsets left. I think that might actually work. I'm tempted to try that. And the other idea is actually just a straightforward like a dynamic programming solution. So I kind of want to try both of them. Well, maybe I should try the dynamic programming solution first, because I think it would actually be correct. However, the problem that I have is I don't think it'll be fast enough. And the other approach where I combine these two ideas of using backtracking for the last few elements, I think that's only going to work for, like, I think there are some cases where it doesn't work. Yeah, I want to say it doesn't work in some cases. So, kind of hung up on this one here. This is gonna be interesting. So we'll read the problem again. Ones and zeros, given an array of binary strings and two integers m and n, return the size of the largest subset of strings such that there are at most m zeros and n ones in the subset. A set X is a subset of a set Y if all elements of X are also elements of Y. Right, so let's try the dynamic programming approach. So the way it's going to work is you've got a vector of pairs. It's not a vector, it's actually it's a vector. Vector of pairs. And it's going to be a vector of vectors. A vector of vectors. And a vector of vectors, and you're going to want, so it's two inputs, so it's going to be the set number, the number of sets, as well as, we'll call it the number of zeros. Now actually this can change. It could be the zeros or the ones, depending on the situation. So it depends on if m or n, depends on which one is larger, m or n. And yeah, we're going to say, yeah, that's fine. Yeah, it depends on which one's larger, m or n. And we're going to say, so we'll kind of decide one or the other, but let's just call it x, right? Instead of zeros and ones, let's call it, or m and n, we'll call it x. So one sort of input will be x, the other input is going to be the number of sets so far, right? So, yeah. And both of these things will increase as we go. Now, we're going to have a pair of two values. It's going to be an integer, which is going to be y, right? And the other value is going to be actually a bit set we're going to use of size 600. Or it really should be m plus n, or excuse me, size of strings. Yeah, the bit set. I want to say that. Hopefully that works. I don't know if that actually works. I think this needs to be known at compile time. So I don't know that, so I guess I'll make it 600 then. Fair enough. Bit set of size 600, pair, a vector of pairs, a vector of pairs, and I might want, I think that's okay, right? So one for the bit set, another for the pair, another for the vector, another for the other vector. Okay. So I will just call this DP, I guess, and we're gonna say have these binary values. We're gonna dump also these values. And you know what we can do? We can actually do the swap here. So call it V, and let's say if m is less than n, m is less than n, otherwise, do it this way. We're going to say for const string s in strings, we're going to v.push back count binary values of s. Now what's interesting is, or otherwise do it the other way around. The smaller one, you actually want to do it the other way around. So it's actually m is greater than n, and we'll do it this way. And then if we do it the other way, we're going to const auto zeros, ones equals count binary values of s. And we would say standard make pair of ones, zeros. So we'll do it this way. So we'll actually, we'll flip the values themselves. I think that works. Hopefully that works. So now we're maximizing. The index is always going to be the one on the left, and the value we maximize always the one on the right. That's how we're gonna so that way this code doesn't have to change at all on the DP side. So what we're going to say is we have an initial vector, which is so auto, or just we'll say standard vector standard an initial vector of these things. And we're going to call this initial, or just like current, do a current vector. That's probably better. So current. And we could do previous as well. I think that's fine. So we'll have like a while loop here, and we're going to say previous is dp.back, and then current is going to be a new variable altogether. We could even do it this way. Make this a reference maybe. It doesn't necessarily need to be a reference, I'm not really sure. And then current is just a new vector. And we would say yeah, let's do initial. So the initial vector is going to have just a single set. It really should be empty, completely empty, I think. Yeah, this is fine. No, this is okay. This is fine. This is fine. The pair is going to be, we can do this. 0, or it's empty, and then the bit set is all zeros, so I can do the empty bit set. Just empty. Or this, I think. Actually, let's do it this way. Yeah. Set or reset. We're going to all, not check, but we're going to set all the bits to true. I'm going to set them all to false, so reset. Yeah, let's just reset. So they're all going to be false. Okay, so we have our empty set, initial, make pair of 0, and the empty set. All right, let's do it that way. Okay, so the first set is going to be empty, right? And we're going to say while I'm actually not sure. You could say while, you could do something like this, while dp.back dot empty. I think this condition would work. Oh, this is not empty. It might be a little bit confusing at first, but I'll explain what that does. Or it'll become clear, I think, later. So we're going to loop over all of the pairs of our previous array, and we're going to build our current array. And the way that we're going to do that is, now what's interesting about this is we actually want the index that we're going over. So we don't necessarily care, so we don't necessarily care what the set is, but we do want the index of, not current, but yeah, previous dot size. Okay, something like this. And we're going to say if, now we could set these pairs if they don't exist by, so we want to have like a default, which would be basically infinite. So okay, so let's do it this way. So we have I, or we'll do X. Let's do X. And let's say we also want to say int target X equals M target Y equals N, right? So if M is greater than N, then we flip that. We're going to say target X, basically swap target X and target Y. And then you don't swap on the other side. So if M is larger, then we actually, the X is going to be the minimum, is the smaller of the two. X is going to be the smaller. So right, so target X. Okay. So I have X is 0, and we also are going to have a dummy value, which will just be, I guess, int min, a negative number. That'll demarcate that we just have filler for that particular part of the array, I suppose. So we're going to say const auto, or yeah, X, let's do Y, and bit set equals, Y bit set is going to be previous of X, we're going to destructure. And we're going to say if Y is equal to int min, it's not equal to int min. Right. We're not going to have any negative numbers for Y. We shouldn't have any negative numbers for Y. So hopefully int min works okay, compiles okay. So y is not equal to int min. Looping over, so we have x, we have y, we have the bit set. Y is not equal to int min. Then we're going to process this x and y from our previous vector, and we're going to say for each value in the bit set, so we're going to say for int ijk, let's call k, or just I equals 0. I also, this is plus plus x, not plus plus I is less than 600, plus plus I. If bit set of I, if not bit set of I, right, so this hasn't been set, then we're going to create a, if not bit set of I, then we're going to take const auto xy or ab from, we're going to destructure v of I, right, which we set up here before. Destructure v of I, and we're going to say sort of add x, add y, or dx, dy. It's probably something like that. Delta, yeah, delta x, delta y. And we're going to say if current dot size is less than x plus dx, all right, so it's going to be new x is x plus dx, and new y is going to be y plus dy. And we're going to say if the current size is less than the new x, or if it's equal to the new x, right? In other words, it doesn't contain the new x. So if the current size is equal to the new x, so if the current size is 5, that means you need to increase, right? So it's less than or equal to the new x, then we're going to expand the, and it's not current, it's new, or yeah, we'll expand the next array, or the target array, the current array. Include this new element. Otherwise, we're going to do if new y is greater than or equal to current of new x. So retrieve current arrays pair located at the target x value, x index. So we're going to say const auto current x, current y. It's going to be v of, not v of I, but current of new x. And we're going to say if current x, if current y, actually current x and current y, they should be the same. We actually don't need this. We could just do current y. Now that's the bit set, so really it's current y and then bit set y. We don't really care about bit set y. If current y is less than the new y, we're trying to maximize new y, then we're going to update current of new x equal to this new bit set, which is going to be bit set of I, or not bit set of I, but okay, bit set. Yeah, it's going to be, this new bit set is going to be bit set and it's going to be bit set and I, and the ith. So actually it's going to be, I want to kind of standard copy the bits, the other bit set. And we're going to set I to true. That's pretty much what's going to happen here. So we're going to, yeah. So, you kind of want a copy of this bit set. I hope that works. I think it does. I think that'll give us a copy as we want. And so now current new is going to be standard pair, make pair of, I make this new pair of new y and this new bit set. All right, that's a little confusing, but hopefully you're able to follow that, all of that. So you've got this back, you've got this current array you're going to build, you're going to loop through everything in the previous, all those indices, you're going to, each of those, there's going to be a y value and an associated bit set for that y value. You're going to process each one of those, and as long as it's not a dummy value, then you're going to loop through all of your bit set, all of your possible set selections. Don't touch the ones you already have looked at. You've already kind of added. Excuse me. Take dx dy from that particular set that we select. Right, we get our dx dy. We get a new x and a new y, depending on, right. Basically, we're considering if we were to add that set, what it would look like. And we check to see, does this new set exist in the array that we're building? If it doesn't, then we'll have to add dummy values, and we'll do that shortly. Add that next. Otherwise, if it already exists somewhere, that means that some other sets, when you add them all together, you get this x and y coordinate that matches. And basically we have the same x coordinate, we know we have the same x coordinate, but we want to optimize the y coordinate. So we're going to take the set that's larger, and so we take what's already there and say, all right, we're going to have this a y value and some bit set. And if this y value is smaller than the y value that we just came up with, for the same number of sets, then we want to switch our bit set to this new bit set, and also switch our bit set to this new bit set, where this bit set is whatever thing we were just looking at plus this bit that we turned on, so this set that we've added, right? So this represents the set that we're kind of already looking at, and or it denotes all the sets put together, sort of the set of sets, if you wish, and then we make a pair out of that bit set representation of the sets and this new y value, and then we set that to where our previous set was, our new x. Hopefully that makes sense. It's a little confusing what's going on here, but otherwise we'll just set it directly if we need to add all of these, what do you call it? We can add some dummy sort of in between variables. So say if int t, we'll call it t is new x. Let's do, yeah, new x and t less than or equal to, actually, yeah, we can do it this way, current dot size, and then t is less than or equal to new x plus t. Does that make sense? So we're going to say current dot push back standard make pair. Yeah, everything. Yeah, so there's like an index that we're looking at to manipulate, and then we only have so many elements, so we need to add elements to get there. And you're going to add an element. So this is an index, this new x, and this is a size. I think it's a little confusing. So the size, let's say the size is 5, the index is 10. So size is 5, and you're going to keep adding from 5 until 10 when you're equal to 10. So you add 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10, you would add 6 elements. And actually the size after that point would be 11, right? It would include this array. Yeah, it's a little confusing, but I think this is correct. So we'd push back pair, and actually we're gonna add one more pair. So this is gonna be the dummy values, int min rather, and excuse me, so it gets overwritten by everything. And yeah, int min, and the bit set is just going to be sort of an arbitrary bit set. Actually, an empty, yeah, an empty bit set it should be. I think you can just do. No, we need to do. We'll just do bit set, dummy set. Yeah, let's do. We'll reset. We'll set it all to empty, I think. So we have dummy sets, and we skip these, by the way. Yeah. Yeah, these get skipped, right? These are the dummy values. These all get skipped. So new bit set, make pair, okay. And finally, right. Oh yeah. So the last thing that gets set here is we have a new bit set equal to bit set. We set I. So new x equal to pair new y. Yeah, it's basically the same. What's new y? We already figured out new y. Yeah. Okay, that's right. Perfect. It's been current array to include this new element. Now, when we stop is when the back is empty. So at the end of this, we push. At the end of this, we're going to push back. So dp push back current, right? And then we sort of start over again. The current gets into a new thing. We just kind of keep going. So it's kind of like I don't know, it's kind of an interesting approach, I guess. Not something I would normally think up or try. So when this is empty, right? That means that. So there are a couple of things I need. This value needs to be less than. So if new x is less than or equal to target x, and new y is less than or equal to target y. So here's the thing. Here's where I say if it's greater than or this is greater than, or the negation of that, then we continue. We don't even process the rest of this. We just jump right to the next thing. Yeah. Skip. Considering adding this set all together. Next vector, current vector. In the case that we have exceeded the allowable resources. Okay. So this part is supposed to guarantee that at some point we won't be able to add any more elements to our largest sets. And actually it's sort of the other way around. This is kind of wrong. We actually want to go the other way. We want to say if new x is greater than or equal to target x, and new y is greater than or equal to target y, then we want to break, I think. We actually want to do a Boolean continue, or just loop equals true. We'll say loop is false. And we'll say int, I guess that, or yeah, I guess. As soon as it's greater than or equal to, and this is greater than or equal to, as soon as both of these are true, right? I actually think it's gotta be greater than both, the way that we're doing this. So we're doing this, we're also kind of doing this backwards. We're actually trying to use the most resources in the fewest number of sets possible. And the solution, the problem is actually going to be the inverse of this. So we would take the total number, so the number of sets required to find this solution, it would be the total sets minus this amount is going to actually be the answer to the original question, which I think is also kind of confusing, but that's kind of what we're going for. So loop is true. You set loop to false if we hit this point, and you would break here. Actually, as soon as a set that exceeds the resource requirements is found, terminate early. Okay. This new x target, new x y target, both of these are greater. Then what we're going to do is loop is false. We break out of this loop, and this loop also we break. Excuse me. Yeah, we would say and loop here. So loop is false here, so this breaks. And then this part, we push current. So I think at the end of this, I want to say the DP size -1 is what we're after. So int, I guess, calculation, I don't know what to call it, is going to be dp.size -1. So like if your resources are just automatically exceeded as soon as you add something, then, which is actually a good question to ask. If it was just like 0, 0, you had to go for, and so you would just immediately exceed the resources, I guess. By the way, the resources we're looking for, actually this is kind of confusing too. This is all very confusing. This is all like extremely confusing. So, wow, no kidding. Oh boy. It's actually not m into n, it's target x target. It's actually the other way around. It's going to be the total of m and n. Oh boy. Going through this twice. Alright, so let's do it this way. This sort of a first round you go through. Oh boy, this is great. This is great. Okay, so we'll start with v1, we'll say, or just z. I don't know, call it z. I'll push back z here, and you actually, well, okay, yeah, we'll do it this way. Push back z here, and you'll have int total n and int and total m and n is the second one, m is the first one. Okay, both are 0. All right, and we say const auto zeros ones is equal to count binary values. One of the reasons why I don't have too much faith in this solution is that it doesn't seem simple enough. I think a real solution would be a little bit more simple, a little bit easier to code. Yeah, zeros and ones, and we would want a standard make pair of zeros and ones, right? And then we're going to total m plus equals zeros and total n plus equal ones. Okay. Alrighty. Now we actually say it's not m and n. It's going to be int. So int. It's going to be sort of residual. Let's call it residual m. It's going to be total m minus m, and residual n is going to be total n minus n. These are actually the numbers we want to work with. So target x is equal to residual m, and target y is residual m n, and then now you say residual m is greater than residual n. Something like this. Yeah. Little confusing. And then now we would say v is just going to be a copy of z, and we swap target x, target y. Or, so if m is very large, then we want to swap, and we're also going to swap the, it's going to be zeros, ones, right? So m represents zeros, m is larger. I think it's the other way around. I think I did this wrong. We want the larger one is the one we optimize. Oh, this is so confusing. Okay. Oh boy. The smaller one we want on the left side. That'll be the target x. Target x is the smaller one. So we are naturally zeros, ones, which is m and n, right? M is zeros. If m is smaller, then actually I think this just stays how it is, right? Maybe I'm crazy about this here. That's extremely confusing. Yeah, if m is smaller, then we want just v equals z, want the smaller ones on the left side. Correct. If m is larger or equal, less than or equal, if it's larger, we want to swap, and we also want to swap, yeah, target x, target y. Excuse me. And also we want to take, we can actually put this where z is now. And we're going to swap these two now. So 1 zeros. So all these values get swapped. And that's what v is going to be. Yeah. So that's really confusing also, I think. It's the residual m and residual n that we're looking for, because like I said, we're actually trying to, it's sort of like the inverse resources we're looking for. Again, confusing. But yeah, so we terminate early when this new x is greater than target x and new y is greater than target y. Yeah. Yes. Ooh, excuse me. Oh boy. Oh boy. And dx dy. So we're looking for x's will be, in the normal case, m is less than or equal to n, the residual, and So we have just zeros, ones for all the pairs. And the target x is just m, number of zeros, target y is, yeah, number of ones. The other case, we swap these two, the targets and the actual values. Okay. So now we say we're going to loop, and so what this calculation, right, we're saying we can just take the size minus 1, right? So the last time we finished looping, we're going to push back current. So if we had one value in there, so that's a little bit confusing too, because we don't necessarily know, excuse me, is it one set or 0 sets or 2 sets? Because we're going to have one set in there to begin with, which is the empty set, more or less. So DP size is going to be 1 always. And then if we add something, DP size is 2, but it's really only one set. So I think we have to actually subtract 2. Yeah. Well, no. If we're in a situation where any set we add at all would exceed, could we be in a situation where we are automatically exceeding? Well, no, right? Because you always need to have, like, M and N are always at least 1, so there's always got to be at least one thing that we add. So let's say we add one element, and we're at target x, target y, and now we want to add another element. It could be the case, by the way, that there are no more elements to add, which would be interesting. I didn't really think about that either. But let's say we add one element, it has a 0 and a 1, and we're at target x, target y. Then we add another element, and we hit this breaking point. So we have our DP size is 1, 2, 3. Yeah, we only added 1. I think it's minus 2, actually. Yeah, we have to subtract 1 for the extra set that we added, and then also 1 for the sort of initial set. The what do you call it? The dummy set. The initial set. Oh, actually, this is wrong. So initial pushback. Yeah, the initial. Yeah, we have to subtract 1 for the initial and then 1 for this extra added set, I believe. Add one set, we have size 2. Add another set, it never gets added, but we're still going to be size 3 anyway. No, it should be 1, because that one that exceeds, we actually want that. We actually want to exceed. We don't want to just be at equal to. We want to go over. So in that case, we have one set and you add 1, or let's say you have 3 sets and you add 1 and you add another second set. You would say 2 sets go over. So 3 minus 2 is 1, so there's only one set that you can go sort of to your maximum, if that makes sense. Hopefully that makes sense. So yeah, so okay, so I think it's just subtract 1. And we also need to consider the case where, yeah, if it's empty, So if we add, so we have just one set. So we add that one set that one time, and then we go enter the loop again. We go through all of these, the bit sets, right? The bits, and they're all set to 1. You actually, we gotta fix that. That's gotta be right. Okay, we did that wrong too. So no, it's not. It's yeah. Okay. I is 0 to, it's gotta be, let's do set. They're all 1s. And then I equals 0 to I is less than strings dot size plus I. And we're going to say empty set. This is going to be the initial set where all the other sets set I, right? Or just I equals true. Yeah. So or equals false. So that's kind of an important one too. Is this set where all the other sets come from, and basically we're using a bit set of 600. So if we're saying not is going to be the filter, then we need to make sure all the bits are set that aren't the ones that we're considering. So that's a minor thing, but almost missed that. I mean, you could do, actually probably better is to do this strings.size here. I didn't think about that, but I mean you could do this here too as well. So don't go through all 600. And what else? The dummy set we don't care about. So right. So we go through the whole set. So we go through that. We say, okay, we don't do any processing here. So our current is empty. Basically, we push that, and it's empty, and then we exit. What does that mean? That means, let's say we had a certain amount of resources. We are trying to use as much as we can to get over the amount. We used everything, and there's still some left over. What does that tell you? So if you had like if you had like 100, and just the only thing in your set was 1, 0, then 100 minus 1 will give you 99, 99. You would just get one thing added to your set. It would be less than or equal to 99 and 99. You wouldn't exceed that. And so you used everything in the set. Normally you would just subtract what's from the calculation. I didn't really think about this actually. What happens in this case? If you can't basically, you don't break the loop here, you break the loop by adding all the elements in the set, and the bit set's full basically. For everything, right? Bits is just full for everything. That's a good question. I don't know. What would you do? Best you could do is a full bit set, and you're actually not greater than the targets. Either one or both. I don't know, man. I really don't know. Actually, I didn't really think about that. If you can exceed one target, but you can't exceed the other. Oh, that's a really good question. I actually have no idea. I don't even know. Not a clue. Uh-oh. I was saying that this might not be correct, this approach, this algorithm. Oh boy. Oh boy. Gotta think about this now. Hmm. Excuse me, sorry, my thoughts are wandering. How do we do this? How do we handle this? Yeah, what if you can't exceed either, or you can't do one or the other, or both? And to end up using, I guess, the whole. Oh, that's so confusing. That's a good question. Oh boy. That's a hard one. I actually don't know what to do here. Okay, let's say you can't do both. Let's just start with that. So you can't do both. So the largest subsequence would just be including everything. But this DP size would end up with basically a full count. Interesting. Excuse me. The target hasn't been reached. That's so confusing. That basically means that, I think that means that I want to say your minimum, it kind of breaks everything. Kind of breaks the idea, because the idea is that you're trying to conserve resource. Ow, cut myself. Shouldn't have done that. Messing around with my soft healing skin here. Sorry, I'm thinking here. I'm sorry. I'm thinking. A lot of, man, I have so many thoughts that are just not fun. Things that are not fun to think about. Why do I screw things up so much, man? I just screw things up so badly. Excuse me, couldn't even imagine. Couldn't even imagine the things that I do. Completely absurd. Some of the things, not all of the things, but enough of the things. Okay, so the problem that I have is if you end up using all of the sets and you still haven't reached these targets, what does that mean? That means you included all the sets, and you got a certain amount, doesn't exceed these targets. Now what we were trying to do is get the smallest set that exceeds this amount, and what that would mean is that there's the largest set that doesn't exceed the, I guess, difference of these values and the total number of ones and zeros, which ultimately would be our m and our original m and n that we're looking for. So that'd be so that's the answer to the question: the largest value that's less than or equal to m and less than or equal to n in terms of ones and zeros, or zeros and ones. Now the problem with that though is if we can never actually get all the way there, then what does that say? That would mean there is no set that can reach that would there's no set that would exceed I don't understand. I don't get it. Because in the case where you just have 1 1 and 1 0, I mean the residual is just 0 0. So, or if you had, let's say you had 2 2 and 1 0, or 200 200, or 100 100 and 1 0, right? Like 1 0 is just one string, and it had 100 100. So if 99 99, and yeah, you wouldn't reach that. You just use everything in the set, which is just one string of 1 0. You wouldn't reach it, and then what does that mean? That's oh no, excuse me. No, because if you do 100 and 100, right, and you subtract 1, subtract 1. No. It would be negative. Yeah. No, you always reach this target. Yeah, because these targets would be negative, both of these targets, in this case. And so actually, your calculation would give you a 0. And so you would take the whole set. No, you're fine. No, that's okay. That's how do these not get reached? When does this not get reached? I was wrong about that. Yeah, because your targets would be negative. Your targets can be negative. They would just always be reached. Yeah, that's fine. But how could you be in a position? Let's say use all the sets. The targets are. Let's say the targets are 0. They're both zeros. The targets are zeros. That means the residual is equal. M and n are equal. That means everything's equal. The targets are zeros. That means everything's equal. The residuals are zeros. That would mean actually it's the first set you try to add. That would give you the wrong calculation though, because that would give you this -1. Yeah, sometimes this gives you the wrong calculation. Sometimes it's right. I want to say when these are equal to the target, actually. I think so. Yeah. Because the other way around works. You could be less than or equal to. Then you don't have to be less than. It just has to be less than or equal. So actually, I think it works greater than or equal to. So yeah, again, if it's the whole sets, then you're automatically at 0 0 before you even begin, and but that's kind of a problem too, though, because That's also kind of a problem because it's so confusing. It's so confusing. The reason for this is if you immediately enter here, you'll still get the wrong amount. You'll still get one extra here on this DP size. It'll be 2 instead of 1, which should be 0. Because we would actually return strings.size minus calculation. That's what we're going for. That's what we're going for. I think say an edge case. Yeah. All right. Does this compile? Let's start with that. I don't know, man. This is so hard. This is so hard. I've been kind of very apprehensive about actually approaching this because it's just so difficult. Or this has been so difficult. Okay, let's take a look at simple test case. Yeah, should be fine on this test case. So where does it break? This is so complicated. There's no way this is right. This has got to be wrong. This is way too complicated, you know? It's way too complicated to be correct. Oh, okay. Oh, we get runtime error straight just immediately. Okay. That's always good. It's interesting that this compiles. I think that's a pretty interesting thing. Check. Okay. So definitely we have a problem somewhere in here. Oh, that might be it. Oh no, well this should be, wondering if this is the issue. Maybe this is the problem. This is just, I did this incorrectly. Oh, that's what it is. I see what the problem is. I think I see the problem now. Hey, oh wow. Ooh, got the right answer. I was not expecting to get the right answer. Really? Cool. Nice. Not expecting that at all. No kidding, and it's quick. It's really quick. Whoa. Whoa. Sweet. 5 milliseconds. That's pretty quick. It's pretty quick. I think this is part of this one. I think these are the same. I think this one is the same as that other one. Yeah, I think it's the same. Alright, let's see how we do on these other test cases. I don't have that much confidence here. Not at all. Invalid test case. Really? Why do these have dot dot dot? Where? What? Oh no, that's upsetting. How did that happen? How did we end up losing our test cases? Oh, come on, man, really? Oh, what is that? What happened? No, why? What? Oh, that's frustrating. It's a good thing I saved these. That's a good thing I saved these. Oh man, that would be really frustrating having to. It's a good thing I saved those. These are all these ones, by the way. I think these are all the same. And these ones, these are supposed to be hundreds of zeros. I actually think if we kept this, which we did. No, we didn't. Oh, you gotta be kidding me. We actually don't need to. This is 100, 100, and 25, 75. This is, actually, no, we should keep them. Yeah, we should get them all. Alright, well, both of these can be replaced with, these are basically just, oh, yeah. These are 100 ones and 100 zeros, and so are these ones down here. 100 ones and 100 zeros. Well, let's come back to that in a minute. One. All right, we're gonna copy 1, 2. So that's 2, 4, 8, 16, 32, 64, 128, 256. And now we need 44 of these, right? So 1, 2, 4, 8, 16, 32. So now we need 12. 1, 2, 4, 8, 12. Okay. Oh, I made a mistake. It's hard to, okay, whoops. That was wrong. Need 44 again. Okay, let's go to 11. Oh, wait, try to get to 11. Oh, okay. Well, all right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we want to go to 44. 1, 2, 3, 4. Did we do that right? I don't think we did that right. 1, 2, 3, 4. Okay. Let's go to zeros as well. One, 4, 12. 8, 16, 32, 64, 128, 256. And now we need, oh, I did this wrong, did I? No, it's 11. Oh boy. Okay. Not 12. 11. 11 4 times. Okay. 1, 2, 3, 4. There we go. All right. Similar thing. 1, 2, 3, 4, 11. 1, 2, 3, 4. Okay, there we go. Don't need these anymore. All right, that's kind of a lot, I realize, but that's what we need. And that'll give us our inputs. Could just word wrap here, I think. It's probably easy to word wrap. All right, let's try that again. See how we do. See if it's compiled, see if we're running runtime errors, see if we're getting wrong answers. Wait till I was afraid of this. I thought this might happen. I was concerned that we might TLE. And here we are. Here we are. I don't know, man. I don't know. I don't know. What do we do? What do we do? Which one of these is TLE? I think they all TLE, or at least a lot of them do. That's a little upsetting. It's a little frustrating. Okay, we'll leave that. Oh man, I'm sad now. There's another approach I want to try, but I don't think it works. Like it's not the best. It's not the best. Okay. I mean, it can be done, but it's like I said, it's not like I said, not the best, But we could try it, I guess. Yeah. So great, great. I don't know, man. Okay. Excuse me. No, the other idea I have doesn't work either. There's another test case that just doesn't work on it. Nope. Will not work properly. last problem. I think I'm probably just gonna look at the discussion. Just give it a rest. I don't want to waste my life on this, man. Quite frankly, I waste so much of my time in my life already as it is. Just waste more of it. I waste so much. I have wasted so much. I waste so much, and I have wasted so much, and I'm extremely sad. It's just been so bad. So bad. So far, not good. You usually have a lot more patience than this, but I'm just kind of upset. I did something really bad recently that cost me a lot. It cost me a lot, and it's just, I can't get over it. I'm like really upset about it. And yeah, it sucks. It sucks. It just sucks, and it's all my fault. It's always my fault, and I can't get away from that. And here I am. Here I am, having done this thing. This wicked and evil thing. I have to bear the consequences of that. It's going to suck. It's going to suck. Anyway, so no, it's too slow. I thought it might be too slow. I thought it might be. What I want to do is just find the right test case for which one is the slow one. Yeah, we have this here. So probably this is slow enough. It's probably one of them. It's probably one of them. Yeah, it's just TLEs. Now the question is, why is it TLE? They shouldn't loop that many times. How many times does this loop? Oh man. Oh, no. No. This is supposed to be done here. That's supposed to finish there. What happened? How come we're at 500? Loop count should be at 250. Oh no. Wait. Actually, no. 500 is exactly correct. Oh no. No, loop count 500 is perfect. How about if loop count is greater than 250? Break. $1,414 milliseconds. I actually think this is the slowest. Maybe this is fine. I actually think if we speed this up slightly, just a slight optimization, then then our algorithm will be optimal, or not optimal, but sufficient. So 450 is too much. Okay, how about 300? 300 loops. Okay. So 300 loops, almost 2 seconds. 350 loops. So that's pretty interesting. So not quite what I was expecting. 1560. Now how about there's another one here. So actually I can modify these to be faster. Believe it or not. Believe it or not, these can be modified to be a lot faster. How about one of the bigger ones, this one? Yeah, something like this. How about something like this? What does that look like? What does that look like? Yeah, it's correct and within reasonable time. How many loops? 89. Interesting. So I think this is a correct algorithm. It's just slow. And we could speed it up for certain test cases by using a frequency map instead of a bit set, which is great. Which is great. The question though is the bit set or the frequency map going to take up more space? That's that's the thing that's not the most obvious. Using frequency maps. Yeah, the problem, like a bit set is a little bit easier to handle because, well, because here's kind of the deal. Like this case, instead of looping over 600 things every time, you'd only have to loop over 2 things. So it would be way faster for the test case we just looked at. However, I don't know that a frequency map really speeds things up so much because you'd have to store the frequency map at every point. So it's a lot of writing and a lot of data to hold, I guess, instead of just a bit set, which is, I mean, yeah, 600. Actually, 600 bits is kind of a lot of information anyway. I'm wondering if we want to store an unordered map everywhere. I'm thinking better would be to store. I have a better idea. Yeah, let's do a vector instead of a bit set. So we'll say we can do it this way. I have a better idea. So okay, residual. Okay, instead of v, yeah, we can use v. That's fine. Let's do instead of v, we're gonna have a frequency map. Build a frequency map. Yeah. Oh, okay, interesting. Okay, I see. I think I understand. All right, let's do it this way. Yeah. Okay, yeah, okay. At a V. So standard map of standard pair of ints to int frequency, total frequency. Say for auto const auto, or just auto p in is it v. We're going to say frequency of p plus plus. And now we're going to rewrite vector of int. We're going to say frequency keys. It's going to be equal to total frequency keys. I think that works. Hopefully that works. Alrighty. Yeah. So now we can say, now do we use a frequency map? Yes. So we want instead of a bit set, we're going to use frequency map. Or just, it's going to be a vector of pairs of integers. And actually, the way this is going to be represented is, it's actually going to be a vector of integers. So this is going to be interesting. But basically, at a particular index in the vector, whatever integer is there, that's going to be like the bit set, I guess. That's going to be how many of those are going to be used. Yeah, so pair, a vector, yeah, it's going to be a little confusing. Instead of a bit set, we're a vector of integers. And same thing here. Hopefully we can do this correctly. Okay, so initially empty set, doesn't matter actually, the empty set's just a vector of integers. You can actually oh wait, I do want to preserve this code though, just in case for whatever reason I want to come back to it. If I got this during an interview, I'd probably just fail it. Like that would just be it. I'd just fail it. It's like, nope, can't do it. Sorry, too hard. Too hard. Sorry. Initial pushback, make pair 0 empty set. This is just going to be a standard vector. Actually, this should have a size. It should be 0, and the size should be frequency keys, that size. Yeah, take that back. That should be what that is. All zeros. Say, okay, both of these are going to be modified. Try to use a frequency map here instead of what we were using before. Yeah, so int. I'll call it frequency instead of a bit set. And now we save not bit set of I. So now instead of the string size, we're going to go through frequency key size. Do each of the frequency keys. And we actually we want to dump all of the just call this F. Yeah, we want to do it this way. Frequency. We actually want to do integers, indices, and then integer to integer. So a vector of integers is going to give us the frequency. So we're going to say for I equals 0 of I less than frequency keys dot size plus plus I. I want to set frequency dot push back F of, really would be I, but it's going to be total frequency or frequency keys of I, F of, yeah, push it through this way. So this will split the, I mean, I guess you could do this, right, this is the values as well. You can just do it that way too, I think. Let's see if this works. The problem I'm having here is I don't know if this is actually going to be fast enough anyway, even after we do all this. I get this feeling it won't be. And even after, it won't be. Key comp, value comp. Well, there's got to be keys and values. Oh, can you not get the keys and the values? Whoa. Extract, erase, swap, and place inserter, assign, clear. Oh, okay. I guess we'll have to do this in a special way. So, also we get rid of the bit set here. So we actually, yeah, so, okay. Frequency keys, frequencies. We're actually gonna do it this way. For auto P in F. We're going to say frequency dot push back F dot second and frequency keys dot push back F dot first. Yeah, I don't think these actually exist, these two functions. Maybe we can check that later, but I don't think, apparently they don't in C++ maps. They might exist in unordered maps and things like that, but not for what we were just doing. So, okay. So yeah, we're going to represent our frequencies with these vectors of integers, and hopefully it'll be less work to do it this way. Yeah. So frequency keys dot size. We're going to say if. Now it's not bit set of I. It's going to be if. And we have a current frequency, right? So this frequency, it's going to be frequency of I. If frequency of I is currently less than frequency, no, I'm going to call this total frequency. Total frequency keys. total frequency and total frequency keys. So total frequency, if it's less than the total frequency here, there we go. Okay, so total frequency keys, and if our current frequency here is less than this total frequency, and the size, by the way, of the total frequency keys, this initial, right, frequency keys that size, total frequency keys that size, yeah, okay. Great, so frequency of I is less than that, then we can add, and V of I is going to be, it's going to be total frequency keys of I, dx di, da dy rather, new x, new y. If we've exceeded this target, then we're done. Otherwise, we're going to expand this array to include the new element, retrieve the current array's pair located at the target x index. And to update this bit set, right, so now instead of, so these bit sets we're going to use now are going to be these frequency maps. Hopefully this makes sense. Actually, the whole thing needs to be redone. So, so this is going to be a vector of integers, a new frequency, goes the old frequency. Now we're going to set I, we're going to take our new frequency of I and increment it by 1. Yeah. And current new, let's make pair of the new Y and the new frequency. There you go. And we do a similar thing up here. So this whole thing is going to be changed. The hope is that using frequency maps, things will be faster, but I actually don't think it'll be that much faster, quite frankly. I think you could concoct a test case such that it's not that much faster. But I think in that test case, actually, the numbers would have to be large enough where you actually wouldn't require that many loops to sort of finish the problem. So I think it kind of works out, but I don't actually know. So this is going to be a vector of frequencies. And so a dummy frequency, and this is actually going to be 0, and it's going to be total frequency keys dot size. Don't need that anymore, don't need to reset, and you could just push back a pair of int min with this dummy frequency. It should never really be processed anyway. And then this is going to be, it's the same thing over here, almost the same thing. All right, does this compile? Let's start with that. Oh, so what is P in this instance? You could technically use an unordered map to do this part, but then you have to write a hash function for this pair, which I kind of don't want to do. I mean, it's not that complicated, but I just don't want to do it. If we can avoid it, it's not really necessary. But the problem seems to be also this could just be we don't need this either. Oh, actually, no, you do want pair of integer vector. Yeah, that's fine. Okay, never mind. That's fine. What's going on here? Are these pointers? Is that what? I don't actually know. It's not a pointer. Oh, I'm sorry. It's not P. It's not F. It's P. Duh. I don't know how I missed that. That's my mistake. I'm getting tired here. Getting a little bit worn out. Loop 0. Okay. Oh, I guess these aren't constants. Total frequency keys. Line 1052. Null pointer of type const value. Where is that happening? Okay, check 1, check 2, how about check 3? I think this is the thing that's causing issues. No, that's fine. We don't get to check 3 though, somehow. Really? Is that the problem? These are the things that are causing issues? These two? Pair of ints and a vector. Y, frequency, vector of integers. Frequency of I. Now, the frequency should be total frequency keys that size. Yes. What does this look like? It should be, I get this wrong often, but I think vector is, oh, it's n in value, I think, not value n. That's my mistake. I think I know what's wrong. There's a way to set this up where you do n and count and value. Count value, not value count. I screw that up a lot. Count value, not value count. That's why we're getting errors, by the way. Shouldn't I shouldn't say it in such a, make that too so exaggerated. That's not right to do. Hey, sweet. Sweet. It worked. And it was efficient. Or efficient enough. I think we were not exceeding the time limit on this one. I think we were okay. Yeah, this one was fine. 72 milliseconds. Wow. 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 Not too shabby. Alright, let's try the one that wrecked us before. The one that was causing problems before. Let's give it a shot. Oh boy. I'm afraid to submit this solution though. I don't think this is going to work. I think this is going to be too slow, this whole thing. I don't think this makes sense. Alright, see, quite a bit faster. Much faster. Yeah, I only have to go to 400. I don't know why. Why did I go to 600 before? Or 500 before? I don't know, that's weird. I don't know what that was all about. I guess the code was kind of off somewhere, somehow. I don't know. Yeah, I don't know. I don't know. Okay. 160 milliseconds. Okay, that's quite a bit faster. So, alright, let's try the whole thing. Let's go for that. Let's see what happens here. Hey, okay. Oh, it just makes it. Whoa, okay. I think 2,000 milliseconds is the cutoff, so we like just make it on some of these test cases. That's interesting. And they're all correct too. That's pretty good. Wow. Wow. Now the question is, does this survive much more rigorous test cases? I don't think so. I actually don't think this will work on the harder test cases. Believe it or not, I think this will actually fail. I think we can go. I got a test case for you that should break it. Break it. Break it. Break it. Break it. It will not survive. It will not survive. All right, ready? We got. Actually, probably you should use a script to generate this. Let me see if we can pull out some scripting skills here. I don't think this solution works as much as I would like it to work. All right, you ready? We're gonna go. Gotta be careful with this. File Explorer. We're gonna go File Explorer. We're gonna go to LeetCode question notes. Okay. Alrighty, LeetCode question notes. We're gonna open a git bash here, and we're gonna write a script that it's gonna generate. I'm gonna write a script. Actually, do I have? No. Okay. Thunder G++. Oh, where? Okay. I was wondering if somehow I had like a C++ compiler here I could write in C++. There's an iota command that would make this a lot easier, but that's all right. That's fine. We're gonna write a Linux script to. We could do an awk script maybe. Awk. Oh no! Ah! What was that? What did I just do? Ah! What was that? That was weird. That was some kind of a key. I don't know what that was. I don't know what that key is for. I don't know. I don't remember. Hopefully nothing important. Hopefully nothing important. Hopefully don't get in trouble. Oh man. That's why I gotta be so careful. That's why I gotta be so careful, man. Alright, let's try again. Okay. Awk. Print hello world. I use this as my personal computer, so it's huh. Wait, what? There we go. Okay. So we can do something like a double for loop. Can we do a double for loop in awk? Try that. I can do like for we just want to do int I equals 0, I is less than, let's do 10 plus plus I of another for loop, int j equals 0, j is less than 10 plus plus j, oops, and we're going to say print hello world. Alright, so we're going to print hello world 100 times. Okay, syntax error, line 1. We could also write the awk script in like a text editor, but I like doing things on the command. I think this we could do on the command line, but oh, I think it's actually this simple. Syntax error. I don't know. How do I awk for loops? Hold on. Hold on. Initialization condition increment body for I. So it's not int. It's just I less than or equal to I plus plus print. Inventory shipped. Okay. Excuse me. Oh, there we go. Ah, look at that. Okay. Can do inside of here. We'll do this block, and we're gonna say x equals this for j. We're gonna say j equals j. Oh no, yeah, j equals hello world, and then hold on. How do we do this? We want to do for opening brackets, closing, or opening braces, closing braces, x equals empty string. For j, x equals x concatenated with hello world. Do that for loop, and close our previous for loop. And close our previous for loop. Before we close our previous for loop, we're going to print x, and try that. Syntax error. Okay, we can do x equals for x. What if we just did like this? All right, they have braces, curly braces. Oh, this needs one of those. I think that's what we're missing. There we go. Okay. And I don't think you necessarily need these braces anymore, by the way. Yeah, you can do print x. Okay, there we go. That's what we're looking for. All right, so you see that? That is printing hello world 10 times. Okay. What we want to print is I equals 0 to 300. We want, yeah, I equals 0 to 300. And j is going to be less than or equal to I, interestingly enough. And, oh, you know, we could do 1 to 300. Let's do it this way. This is better. Equals 300, and then j is from 1 to I. And we're going to say, not hello world, but we're going to add a 0. And here we go. And now we want to put that in a, we'll call it temp1.txt. And then we want to do the same thing, but for ones, and put that in temp2, temp1.txt. And now we open temp1. There you go, you see that? What we want to do is actually what do we want to do? We tr the new line characters. Will this work? Can I do this? Oh, we can. Oh, that actually works. No kidding. Okay. So one thing we want to do is modify our awk script here. And we're actually going to remove temp1. Where's our awk script? Here we go. So we want to go to 0. And we actually want to print this. If we can do that. And do that with 0. I can't. No. We want x concatenated with can we do this? It might just be the shell. No. How do we get the quote characters? Double quotes. How do we get the double quotes? How do we do that? Can do a equals a quote, maybe, AXA. Double quotes. Oh, look at that. Nope. Interesting. Really? Interesting. It's in my pocket. All right. It's time for bed. It's time for bed. Okay. How are we doing here? so interesting. AXA. Nothing. Now, how is it? Do you do this? Nope. Can you do this? Oh, that works. All right. How about this? This one. There we go. That's what we're after. Okay. We don't need this A anymore. So fun with awk today here. And now we want to add ones. I want to see zeros. And ones. And we want to just cat temp1 tr new line character with a comma and set that to temp2.txt. It's temp2.txt. And we're going to vim. It modifies temp2 slightly. Add one of these, and at the end, one of those. Oops. Yeah. And that's it. Okay. Now, if we explore here, we can temp2, and we can grab this. And I think that this is a test case. It's a valid test case. We'll do 100, 100. I do believe this is a valid test case. I could be wrong. Oh, I am wrong. There can only be 100 strings. Oh, shoot. I did it wrong. Did it wrong. Okay, well, we have 600. I want to get down to 50 then. Interesting. Very interesting. I don't know. This is definitely wrong though. Yeah, there's 300 of each. Can only have really 100. I don't know. This is actually really straightforward though, because that's a valid test case. Can we just remove a big chunk right in the middle until this is a valid test case? I don't know that we can. I don't think so. I don't think it works like that. Look how much I have to remove. Alright, delete all that. Try that now. Okay. Great. How many of these can we remove? Let's remove a bunch. Let's remove a few. Alright. Are we under 100 now? I think so. try this. We don't want to ruin this. This is probably too many. It's probably too many. But the idea is that the frequency map gets kind of messed up here. Ah, 1 in 100. Okay. All right. Keep modifying this here. Move a few more. Go to here. How about that? Look at that. Look at that thing. It's a monster. It's a monster. Okay. Oh boy. Still going, huh? Yep. Still going. Still going. Okay. We'll take off a few of these earlier ones, I guess. Leave the earlier ones. Let's get rid of these ones. I don't know how many things we got to remove to make this work. Probably a lot. Probably quite a few. Oh boy, how much time we spent here? 2 hours, okay. Still not good enough, okay. All right, not there yet. Not there yet. These are the ones we can close, I think. You can see why I'd want to do this programmatically. You can see why I might want to do this with a program. All right, take out a big chunk here. And take out a chunk over here. Just a few more of these. I don't actually know how many we got now. I do not know. Oh, come on. It's killing me. How about we just keep removing stuff until it works, and then we'll copy that one back. Excuse me. Oh boy. Okay, how about that one? I've had to shave away a lot more than I realized, or would have realized, or otherwise thought. Let's do like a couple more of these. Wow, that would have been at this for a while if I kept copying it back and forth. How many of these gotta remove? this one now. Should I just remove like half of them? I don't know how many I gotta remove. Let's remove all these. Let's remove all of these. Oh man. Wow. I mean, I had 600 of them, right? It feels like there's so many. Feels like there's so many. How many of these do I have to remove? Man. Still more than 100. How is that possible? It feels like there's not 100. But somehow there's 100 of these. Really? Really? There's no way there's 100. This is not 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, it's huge. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41. It's 41. There's only 41 here. What? How? What? Is it something else that's causing the problem? Oh no! Oh, now we TLE. Oh, what? We were doing so well. What? No. Oh, don't tell me that. No, we were doing so well. What do you mean now we TLE? What is this? Oh, we're so close. I can't believe it. I think we lost. I think this doesn't. I think this doesn't work. I think we have TLE. Oh man, this is not 100. Definitely not though. This is definitely not 100. What? 1 and 100. Oh. Oh, I got this wrong. The number of strings could be 600, but the length of each string is gonna. Oh man, why do I screw everything up, man? I get everything wrong. I always get everything wrong. Oh boy. Oh. Okay, that's my fault. So there could be 600, but they have to be. But okay, I get it. I get it. I get it. I get it. Wow. Okay. So all these ones in the back need to go, basically. I was trying to understand what was wrong. I see now. All right. Well, I think this one's not going to be much of an interesting, not be a particularly interesting test case then. Man. Glory, glory. Oh, I don't know, I mean, we could hit the submit button just for the sake of it, but this seems like this might be a bit slow. This might be a bit slow. Is there maybe something I can do to speed this up slightly? Like maybe I can, when we make these pairs, we can do, or these dummy frequencies. Can they just be like null pointers? Or just something real simple. That doesn't really help much. That actually doesn't help that much. Yeah. I can still just randomly TLE. I don't think we got this. I don't think so. I think there are definitely test cases where this would fail on. Should we go for it? Let's go for it. Let's just try, see what happens. I don't think we got it though. I think not. Probably TLE somewhere. Oh! Ho! We did it! Are you kidding me? Is that real? We did it. Whoa. Wow. I can't believe we did it. No kidding. Seriously? Let's try again. No. No way. We did it. Hey! Oh! Dude, I was at that for like 4 days, for like a week. You gotta be kidding me. That's... Wow. We did it. It's correct, and we did it. Can't believe we did it. We did it. Hey! Hey! Success. Great success. Great success. Wow. How you like that? Now, could I ever do this in an interview? I mean, technically, yes. Probably not, though. Probably not. Excuse me. That's a heck of a solution, man. Whoa. Whoa. There's so many pieces to it. I can't believe it worked. It actually worked. I can't believe it. Now, might find out that this is just like an inefficient way to do an easier to code and more efficient dynamic programming solution, but somehow we did it. I don't know. I don't know if that's just the test cases they chose or what, but it works. It worked. We did it. Used a lot of memory and a lot of time. We got there. Maybe there's things here that are redundant. Maybe that's the thing. Oh, that's too funny, man. This is great. This is great. This is great. Wow. Wow, we will, king of the castle. Wow, we will. I can't believe this works. I actually just can't believe it. I don't think, like, I still don't believe this works. I still think this is wrong. It's right, but it's wrong. Somehow it's wrong. There's no way. This is what? I can't believe we did it. I can't believe it. Total disbelief. What? Excuse me? What do you mean this works? What do you mean this is correct? No, it's not. No, definitely not. No way. No way. No way. Brother, this is so complicated. Wow. I can't believe we did it. Somehow it works. Somehow it works. I don't know. Let's try again. I can't believe it. Oh, when you sang to me. Oh, when you sang to me. I can't believe it. Oh, when you sang to me. Oh, when you sang to me. I can't believe it. Oh, when you sang to me. Oh, when you sang to me. I was thinking there's like a test case where you just randomly generate a string of like, not size 100, but something approaching size 100, like, and randomly generate these 600 strings. I mean, we did it, man. I don't know what to say. Yeah. Wow. Okay. All right. Okay. That's good. That's a positive thing. That's amazing. That's astounding. I can't believe you did it. I'm shocked. Actually shocked. I mean, it's slow. It uses a ton of memory. But we got there. Hey, man. We did it. That took a really long time. That took a really long time. It took a really long time to figure out. A really long time to code. Quite a few mistakes, I guess, when coding it. Quite a bit of is slow. It only beats 10% of the solutions in terms of time, and uses a ton of memory. It only beats like 5% of the solutions. So it's definitely one of the more like heavyweight. Probably not the best solution, but it works. I mean, hey man, I don't know what to say. It works. If it works, it works. What are you gonna do? What are you gonna do? So I guess we ended there. Yeah, I don't know, man. Okay. Oh yeah, that was my alarm to go to sleep. So that's that. It's time for bed. Wow. Yeah. I just want to kind of bask in this for a few moments. Just great. What's the plan for me? I don't know, man. Dude, my life is just a mess. I'm grateful to God that I'm saved. Just praise God. That's the only thing that matters. Everything else I do, everything else I think is just meaningless and vain and a failure. That's the thing. I'm just like an utter failure. I'm like I fail at everything horribly, and I just cause such problems. And I ruin things for myself in a way that's just hard to fully appreciate how much I ruin things. And it's so sad. It's a tragedy. It's sad. It's awful. Yeah, man. I'm so sad. Just so sad. How much I tend to ruin things. How much I ruin things. How much I tend to ruin things. It's awful. That's it. It's awful. It's just really bad. It's just really bad. That's it. I have a tendency to ruin things. That's all I can say, all I can think. Yeah. Yeah. Wow. Anyway, sorry. That's totally unrelated to this problem. I'm just glad I finally got there. It worked. I can't believe it worked. I had an idea, and it worked. Amazing. Can't believe it. Unbelievable. Unbelievable. What I was thinking was maybe you can write like a hybrid solution. That was the other idea, was that you have like for most of, I guess, the problem, you find like the things that take the least resources, but then when you get to a point where, I don't know, there's only so many sets to pick from, or there's only like a small amount of resources left to consider, then you actually do like a brute force approach on like a small portion. Yeah, something like that. That approach is like, I mean, you could do it that way, I guess, but it's maybe not the best way. I don't know, maybe like a depth first search where you try to optimize for the things that use the least resources, and you just take the first thing that you come across that uses all the resources, I guess, or yeah, you terminate early if you come, yeah, if you use all the resources, or I don't know. Somehow go backwards. I don't actually know that I don't actually know what to do. Like I said, I actually kind of ran out of ideas. Like, I don't have a good. I have to look at the discussion to see what other people did, what other people did regarding like a smarter depth first search. They might have smarter dynamic programming solutions. That might be it as well. I can't believe we did it. We did it. We did it. I can't believe we did it. I can't believe it. Wow. Wow. Okay. Well, anyway. All right. Yeah. We like just barely made it too. All right. I'm gonna go. Thank you for watching. Take care. Have a good rest of your day.